Let us continue doing problems based on aromaticity. And the next problem I want to do is a classic problem, which is asking which is more basic, the molecule Pyrrole or Pyridine. Pyrrole looks like this. Nitrogen. It's a 5-membered ring, 2 pi bonds, a hydrogen. Pyrrole. And then pyridine, I'll draw it underneath. Pyridine looks like this. We have another nitrogen in a ring. That is pyridine. Maybe you've seen pyridine before in previous reactions where we need to use a base. But why pyridine? Okay, why not pyrrole? Or can we use either one? Can both of them be very good bases? Well, we want to understand what a base does, right? A base grabs a proton using a lone pair. We're also in the unit of aromaticity, where it's important for us to, at times, figure out whether that lone pair is part of the pi system or not. My suggestion is let's draw any lone pair on these molecules that we know exist. So here's a 1 on that nitrogen, and here's 1 on this nitrogen for pyridine. Well, right now I'm not sure exactly where this problem is heading or how to approach it, but why don't we assign whether these molecules are aromatic or not? We could even be more specific. Are they aromatic, anti-aromatic, or non-aromatic? Well, let's take a look at Pyrrole. Pyrrole is that situation where you have an atom that looks sp3 because it has 4 areas of electron density. Okay, and you were originally taught that those are tetrahedral atoms. But for aromaticity, we want to pretend, well, what would happen if I made this sp2? Because for this molecule to be aromatic, all the atoms around the ring, or all the atoms that are making up the ring, have to be sp2. So if N is sp2, then we satisfy rule 1 that all atoms that make up the ring are sp2. It's a 5-membered ring, and that's my cutoff. If the ring is 5 atoms or less, you could essentially call it flat. Sure, it could pucker a little bit, but it's not going to pucker so much that the p orbitals are not going to be interacting or aligned with each other. So essentially this is flat. And now, how many pi electrons does Pyrrole have? We count 2 here, and we count 2 for this pi bond on the right. That's 4. But remember in the previous video where we had a nitrogen that has a lone pair and 3 single bonds? That we could make this nitrogen sp2, that lone pair will be in a p orbital. Why don't we do that here? It would be worth drawing the cartoon. There. Nitrogen. Okay. Every atom in the ring is going to be sp2, even the nitrogen, because that's our proposal, right? That's what we're checking whether this is beneficial or not, whether we should keep it as sp3 or make it sp2. We know now, just via resonance, that for this to participate in resonance, that lone pair has to be in a p orbital because, well, no, that nitrogen has to be sp2 because we need a p orbital to overlap the other p orbitals. But let's finish this drawing because we have a bond here to hydrogen. Okay. Now I drew that nitrogen as an sp2 atom, and let me see where all the electrons are. You know that nitrogen has 5 valence electrons. One of the valence electrons is helping make a bond here, a sigma bond. So that's in an sp2 orbital. An electron here is in an sp2 orbital making a bond to this carbon up here. and then there's an sp2 orbital going to the right. So if you want to just isolate what's happening with the nitrogen, right? You've done this exercise before. There are 3 sp2 orbitals, right, for an sp2 atom, and there's 1 p orbital that's not hybridized, the 3rd p orbital, right? 2 of the p orbitals hybridized with the s, and the 3rd p orbital remained unhybridized, and you have this dumbbell, what a regular p orbital looks like. Okay, so I'm not going to label all of these. Let's put the pi electrons. So we have 2 pi electrons on the left, but we'll call this the top double bond here. We have 2 pi electrons on the right, and we'll call it these 2 carbons. Nitrogen has 5 valence electrons, and let's look at our isolated nitrogen. We have an electron here, here, and here, making our sigma bonds, right? That nitrogen is trigonal-planar because it's sp2, and we're showing the 3 sp2 orbitals. But nitrogen has 5 valence electrons. See that lone pair? That's electron 4 and 5. But the only space it has is in this p orbital. And I'll just put both electrons in the same lobe. So let me translate that up here, and we have this. Okay. So by having nitrogen in an sp2 hybridization state, we're able to get that p orbital of nitrogen to be overlapping the p orbitals of the neighboring carbons. With that being the case, those 2 electrons are now delocalized in what's called the pi system. And if it's part of the pi system, those 2 electrons are part of the pi number, how many pi electrons. So we have 1, 2, 3, 4, 5, 6. There are 6 pi electrons. And if you count here, yes, you would have to know, either by drawing the cartoon or understanding that the only place where this lone pair is a p orbital, if the nitrogen is sp2, then that is part of the pi system. 1, 2, 3, 4, 5, 6. My conclusion for this is that this lone pair right here, there are 2 conclusions, is part of the pi system, and therefore delocalized. And we want it to be part of the pi system because that kicks us up from 4 pi electrons to 6, and you know that this satisfies the requirements for a molecule to be aromatic. And that's why this nitrogen, you have to assume that it is sp2 hybridized, because the molecule wants to be aromatic. It's more stable when it is aromatic. Where the stability comes from, again, that's was covered in a previous video, so we're not going to worry about that. Okay, Pyrrole is aromatic. So what? How does that help us in deciding whether it's more or less basic than pyridine? Well, I think it would be good for us to figure out, well, what orbital is that lone pair in? And if we draw this on its side, just like we did for Pyrrole, I have now 5 carbons. Let's see if I could do this without overlapping. And here I have a nitrogen. Okay. Well, this is interesting. See, for this one, this is incontrovertibly sp2. You cannot make this sp3. There aren't 4 areas of electron density. So, I mean, that's good in terms of trying to get this to be aromatic. And that's also good in the sense that we don't have to make a decision about this atom. It's only the atoms that have a lone pair and look sp3, whether you want them to be sp3 or sp2. Because they could switch to sp2 to be able to do this type of delocalization. But this one, this can't turn into an sp3 atom, right? There's not 4 areas of electron density. This geometry around nitrogen has to be trigonal-planar, the electron geometry, right? The electron geometry. Okay, let us draw our p orbitals. Right now, I still don't see how this is relevant to our question, which is more basic. But let's see if by drawing this we get an idea. That nitrogen is sp2, so we're drawing something similar to this nitrogen here. We have a sp2 orbital jutting out, okay, just like we did here, but in this case, that sp2 orbital was participating in a sigma bond. This sp2 orbital is not bonded to anything. Let's fill in our electrons, and we're going to start with this double bond right here. I'll call that double bond between these two carbons. Okay. What about that double bond? That double bond is between these two carbons. Okay, we're just going around the ring. So here's an interesting thing that's fundamentally different than what we've seen here and in a previous video with nitrogen atoms, is that we have a nitrogen atom that has a pi bond. You know, for this example here, I was able to put an alone pair in this orbital. What am I going to put in this p orbital? Am I going to put the lone pair? If you look at your drawing, it's telling you that you have a pi bond between the carbon and the nitrogen. So there has to be an electron here contributing to the pi bond, and there has to be one electron here from the nitrogen to make that pi bond right there. Oh, that's something new. It's new that we're not putting a lone pair in that nitrogen. But that was a decision made for us already because the structure says that that nitrogen already has a pi bond. So in this case, the p electron, or you could even say the p orbital, is participating in forming a pi bond. We don't see that up here. Okay, we don't see that up here. Now it can if we do resonance. All right, but in this picture, there's no pi bond to that nitrogen. Nitrogen has 5 valence electrons. Where are they? We have one here for the sigma bond. We have one here to make the sigma bond. We have one here to make the pi bond, and we're missing 2. Those 2 are over here. So this is different than Pyrrole. The lone pair for pyridine is in an sp2 orbital. Just keep things straight. That sp2 describes the hybridization of nitrogen. This sp2 tells you what orbital the lone pair is in. Okay. But is this molecule aromatic? I think that's what we want to answer first. 1, all the atoms, including that nitrogen, because it only has 3 areas of electron density, has to be sp2. Check. Number 2, flat. Is it flat? Well, if we want it to be aromatic, we're going to make it flat. And it can be flat. There's no steric hindrance. Now, the only reason why I wouldn't want it flat is if it becomes anti-aromatic. Okay, but we haven't checked yet. We only are up to rule number 2. Rule number 3, how many pi electrons are there? You can either look at your line structure or you can look at your cartoon. If you look at the line structure, you have 2, 4, 6, and you're not counting the lone pair because the lone pair is in an sp2 orbital. So by looking at the line drawing, I have 6 pi electrons. But look at your cartoon. Where are the black dots? Let's start here on the far left. 1, 2, 3, 4, 5, 6. Oh, 6 pi electrons too, just like we had for Pyrrole. Our conclusion is that pyridine is also aromatic. Uh-oh. Well, nuts. I thought we were supposed to see a difference between Pyrrole and pyridine to figure out which one's more basic. Look carefully. We do see a difference. The difference is right here. The lone pair of pyridine is isolated in an sp2 orbital. The lone pair of pyrrole is actually part of the pi system and delocalized. So between those two situations, which do you think is more likely to grab a proton? Because your base, if you recall, would have a lone pair and you are grabbing the proton of an acid. The analysis here is that this lone pair is more likely to grab a proton because this lone pair is, I call it, preoccupied. It's busy circling around the ring. It's busy being delocalized. It's not really, a full lone pair. My conclusion then is the lone pair of Pyrrole is preoccupied, being part of the pi system. Why is it being part of the pi system? Because it has to be for Pyrrole to be aromatic. It wants to be part of the pi system to kick up those 4 pi electrons up to 6 pi electrons. Pyridine doesn't need that. And actually it can't do that because the lone pair can't fit in that p orbital. So it already has 6 pi electrons, and all the p orbitals are already busy. They're already participating in pi bonds. So that lone pair is just hanging out. It's just sticking out, waiting for an acid to fly by so you could grab its proton. The conclusion is the lone pair of Pyrrole is preoccupied being part of the pi system. Therefore, right, 3 dots means therefore. Therefore, Pyrrole is less basic. It's less likely to use its lone pair to grab a proton than pyridine. Did we answer the question? Which is more basic? Pyridine is more basic. Pyrrole is less basic. Because, again, the lone pair of Pyrrole is preoccupied. Also, we could say the lone pair of pyridine is in an sp2 orbital that's not part of the pi system, so it is fully available to grab a proton, to be a base, essentially. Okay, that is a classic problem. There are many ways that a professor can ask whether you understand this concept or not. Okay, they could give you other different molecules that use the same principle. Is that lone pair preoccupied, or is that lone pair off to the side that ready to grab a proton? All right. Okay. I have some other acid-base problems in mind. Let me show you those. So here, knowing aromaticity helps us predict basicity, how basic a molecule is. Okay, and again, don't get caught up in the fact that they're both aromatic. It's not that we're not using directly whether something's aromatic or not to determine basicity. We're asking ourselves, when the molecule is aromatic, where is that lone pair? That's the important question. Okay. That's for this type of problem. Why don't we look at another type of problem? Which one is more... Hmm, which one is more acidic? Give me 1 second. How about this? Huh. Okay. When we have a molecule like this, what is the pKa of any of those hydrogens? The, the hydrogens here are all on a tetrahedral carbon, and it's very hard to remove a hydrogen off of a tetrahedral carbon. It represents one of the most or the least acidic protons that we have. The pKa is around 55 to 60. Let me go with 55. Okay, so this is an alkane, and if you need to draw it, it's to rip off one of these hydrogens. I'll put a square around it. Okay. Well, what about if we had a hydrogen off of a double bond? Okay, it's still off of a carbon. Do you remember the trend in this case? The pKa goes down quite a bit, but it's still not very acidic, right? The pKa here is around 45. And then just to finish the trend, you know that for a triple bond, or hopefully you know that this is the most acidic out of these three, but it's still not too acidic. It's a pKa around 25. Oops. 55, ouch. 55, 45, 25. So my question is, I have here a hydrogen that's also off of a carbon. And when the pKa of this proton is measured, ooh, it drops. It drops down to 16. It's as acidic almost as water or as an alcohol. Now, are these analogous? Actually, if I want a very analogous molecule, maybe I should have compared it to this. An allylic proton. Okay. For the allylic proton, right here, the pKa is around, it's around 36. So it doesn't drop that much from a regular alkane. Even though, remember, if you deprotonate at this position here, that lone pair can participate in resonance. But that resonance doesn't really add a lot to the stability of the conjugate base. Why is this so low? Why does it want to lose this proton? Well, let's see. Let's give it a base, and let's give it a strong base, NaNH2. Okay. And what is the result? The result is this molecule here. It seems like this molecule is very, very motivated to lose its hydrogen, to act like an acid, to have a base grab that proton, because look at the result. Look how stable the result is. Do you know why I'm calling this very stable? Think about the unit we're in. This molecule is actually aromatic. What did it start out as? We haven't seen a lot of these examples because it's pretty obvious. This atom right here is sp3. So we already have an atom on the ring that's not sp2. It cannot be aromatic, nor could it be anti-aromatic, right? For something to be anti-aromatic, your atoms still have to be all sp2. So this is non-aromatic. It's not, it's not particularly unstable, but also it's not particularly stabilized. So when you think of the energy diagram, it's high, up, and then when you do the reaction, it drops because you're forming a very stable aromatic molecule. That is the reason why this proton is so acidic, because out of all of these cases, right, you could lose any of these hydrogens, you're not going to make an aromatic molecule, right? Even this one, because you have sp3 carbons here. It's only this one where you can make an aromatic molecule by losing that hydrogen. Okay. All right. How about this? Do I have time? Yep. Let me do one more example. Right, these are examples where we're using the concept of aromaticity to help us figure out reactivity, to help us figure out if between two molecules, which one's more basic. It helps us explain, in the last case, why a molecule can be so acidic when normally you wouldn't expect that for analogous molecules. How about this? We haven't seen a 7-membered ring, actually. We've seen 3-membered rings, 4-membered rings, 5-membered rings, 6-membered rings, but we haven't seen 7 yet. So which is more stable? Cycloheptatrienol anion or the cation version? Question mark. Okay. Let's go for the anion version first. That's the 7-membered ring, and triene means 3 triple bonds. Sorry, 3 double bonds, and it's an anion. And for this to possibly be aromatic, we would have to put the anion up here. Okay, I don't know for a fact it's aromatic. Okay, but I'm going to put it up here because all the other carbons are sp2. So maybe if this is sp2, it'll be fine. Why don't we analyze this first? So this is a very good example that we haven't seen. Not only is it 7-membered ring, but here's another example where we get to decide whether we want this carbon to be sp3 or sp2. Okay. Again, for it to participate in any resonance, it has to be sp2. But if by making this sp2 it's not beneficial, then we have to revert back and say it's sp3. Because look what happens here. If the carbon anion is sp2, we have all the atoms in the ring sp2. Great, check. I'm not saying that the molecule is flat. What I am saying is the molecule can be flat, because I'm going to try to see if this molecule can in any way be aromatic. So yes, it can be flat. What about the pi electrons? I definitely see 6 pi electrons, 2, 4, 6. But do I include these? I don't want to include them, right? Because if I include them, I go up to 8 pi electrons. But you don't choose that way. We already chose that this be sp2. We have to know where is that lone pair when the carbon is sp2. When the carbon is sp2, right, just like we did for nitrogen, we have 3 sp2 orbitals, and we have a p orbital. Carbon has 4 valence electrons, okay, but it's negatively charged, so we add an extra electron. So that's one way to analyze this. Or just look at the picture. You have a sigma bond to the left. So let's say it's this orbital overlapping with a carbon orbital here. There's one sigma bond. There's a sigma bond to the down here, to the right here. There's a sigma bond to the right. So there's an electron there. There's a sigma bond to the hydrogen. We'll call this one the sp2 orbital that's combining with the s orbital of hydrogen. And we have a lone pair. There's no place else to put the lone pair. I really don't want the lone pair to be in a p orbital because that will kick me up to 8 pi electrons. But I have no choice. If that carbon is going to be sp2, that lone pair has to be in a p orbital. It has to be. So yeah, unfortunately, I have 8 pi electrons. So that's not a Huckel number. What this tells me is that if that carbon anion is sp2, this is anti-aromatic. Does the molecule have a way to not be anti-aromatic? Yes. Since I don't want to be anti-aromatic, therefore we're going to consider the C minus to be sp3. And once we change that into sp3, you can't be aromatic or anti-aromatic. You have to be non-aromatic. This molecule is non-aromatic. My question is, which is more stable, the anion or the cation? That's non-aromatic. So I'm wondering if the cation is aromatic or anti-aromatic, or it could also be non-aromatic. I did not draw this as well as the first one, but it's still 7 members. You could even put dots. Okay, and now instead of an anion, I have a cation. You know, the cation, that carbon, I've said this many times already, it has to be sp2. Carbocation carbons are always sp2 hybridized. So in terms of our rules for aromaticity, all those atoms are sp2. Number 2, it can be flat. Okay. And number 3, how many pi electrons? There are 2, 4, 6 pi electrons that I see. There's actually no lone pair here, so I don't have to worry about adding 2 more electrons. All the atoms are sp2 hybridized around the ring, so we're good. This is 6 pi electrons. Check. This molecule is aromatic. The question was, between those 2 molecules, cycloheptatrienol anion or cycloheptatrienol cation, which one is more stable? Well, this one's easy. It's the one that's aromatic. Okay, and we're going to know that this as I almost said anti-aromatic. We're going to know this as non-aromatic because it was headed towards anti-aromaticity, but the molecule is surveying, right, the different hybridizations between sp2 and sp3, and once it hits sp3, it realizes, or it lowers in energy compared to anti-aromatic hybridization, and the molecule assumes an sp2 hybridization for that carbon, and it is non-aromatic. Okay, all right. So those were 3 pretty good examples of how you could use the concept of aromaticity to figure out acidity, basicity, and here stability. The last video, we haven't done any reactions, right? Or we haven't seen any new reactions. We've done acid-base, but we haven't seen any new reactions. The last video in this unit 13 will be some review reactions and some new reactions where we're going to do reactions that are 1 atom off of the benzene ring. Okay. And we'll take care of that in the next video.